Okay, so this video is about the first of two intractable math problems. And we're gonna be looking at the integer factorization problem and the RSA protocol that uses it. So this is the integer factorization problem, and it's pretty straightforward. You have two very large prime numbers and you multiply them together. Now, when you do so, it's very easy to multiply them together, but it is computationally impossible to start with a result and try to reverse engineer or back into what your original two numbers were. That's the integer factorization problem. To pick a good P and Q is trivial and quick to do, but the only way to try to go backwards, and remember, n is public knowledge, the only way to try to go backwards is completely infeasible. And when this concept was first introduced, it would have required 10,000 years to try to reverse engineer a certain size P and Q. So we'll do a couple of examples on why this is the case. So if you're given a prime number, to determine what numbers have been multiplied together to make that, if any, you have to start at the very first one, first prime number, and you just check it. And if not, you go to the next number and you check again. Or another approach, or another example is if you have success and you're starting with a number, you're trying to figure out what numbers multiplied together make that. So in this case, you start with 2 and you have success. Like, yes, I have found a factor of 72. One of the factors is 2. It results in a whole number. So now you've got an 72, and so now you have another number, 36, and you have to factor that one again. So again, you check, you get an answer, and so on, and you find all the prime factors that are inside of that number. So, and then for the last one, in this case, you're checking 121. In this case, you had to check 6 numbers. But there's another point here is once you reach the square root of n, there's no need to keep going up. So if this is divisible by a number higher than 11, as an example, you would have already found that number before you got to the square root of whatever your n was. So as a whole, looking at just the single digit numbers 1 through 9, the average number of checks you would have to do to factor them or check the factors is pretty small. It's 1.6. Now we go to a double digit number, and just take 71 as an example. You would need to check all the lower primes up into the square root, and this results in about 5 checks. And generally speaking, for double digit numbers, you're going to need about 5 checks. So every time now that you add a digit, you can start to see the effort required to factor is growing at a much larger rate. And computers are looking at this in bits, and there's an equation that describes this. So this is the amount of effort you would need to factor, to find your secret numbers P and Q, if you start with a publicly known number of n. And this chart here just shows the start of the exponential growth. Once you reach 10 bits, you would need almost 100,000 checks in order to factor and figure out what P and Q were. And when RSA was first published, there was a 200-bit n was recommended. And at the time, the most advanced computers in the world would need 10,000 years to factor P and Q. And then the last point was it's very easy to increase the size of n. It's easy to increase P and Q, easy to make these numbers and multiply them together. So it was easy to increase this, and when you do so, the number of attempts that you would need to factor would just explode exponentially. So this protocol was considered safe against all the future advancements in computer power and speed. So this is the first part of RSA, and now we need to go into another part, which is some of the special math that applies to prime numbers and helps us create our decryption components. specifically D for decryption. So from the top, these are just some key definitions, and what relatively prime means is you have two numbers that do not share a common denominator. So for example, 11 and the number 7, or really any of these numbers, but 11 and 7 as an example, there is no number that divides both 11 and 7. It shares no common factors. And reshuffling the slide, and this brings us to Euler's phi, which just counts the integers that are relatively prime to a given number, and we're going to look at an example of this. So this is Euler's phi for several numbers, and these are the numbers. These are all the numbers that are relatively prime here in this column on the left. These numbers here are all relatively prime to it, and this is the total count of those numbers that are relatively prime to it. So Euler found this relationship. You have a prime number, the phi of that number is just the prime minus 1. And then there's also this multiplication connection between two numbers as well. And we'll do a quick example to show what this looks like. So if we have two prime numbers, 3 and 5, the phi of those numbers are 2 and 4 respectively. Multiply the phis together here and you get 8. Multiply the primes together, you get 15. And the number of numbers that are relatively prime to 15 is 8. That's the same number. Euler gave us that. And another quick example, your primes are 5 and 7, your phi is 4 and 6. 4 times 6 is 24. The phi of 5 times 7 is also 24. And now let's relate this now to our P and Q. So N is our P times Q. And we know that, and we know the value of P minus 1, and we know the value of Q minus 1, because these are our secret numbers. But no one knows P minus 1, Q minus 1, P, or Q. No one's going to know these numbers just given N due to the difficulty of factoring. And likewise, no one's going to know, I'm not sure on this slide, but the point I wanted to make was these numbers remain secret. And then there's another theorem, Euler's theorem, that relates our N, our phi of N, which is secret, and our message, which we're going to call M. But first we need to get into a little bit of the modular arithmetic. And modular math or arithmetic is really just a way to loop together sets of numbers and do calculations. And it's nothing more than doing math, say, with a clock. So if we took 7 p.m. and wanted to add 30 hours, how would we do this? And you could, pause the video if you need to and do the math in your head real quick. But it is pretty straightforward. We're just going to all intuitively just add 24 hours. It takes us to 7 p.m. the next day. And then we know to add 6 after that. It takes us to 30. So 7 p.m. plus 6 hours is 1 a.m. And with modular arithmetic, here's how we would describe that. And here the 12 is called the modulus. 30 mod 12 has a remainder of 6. So that is how we describe that with modular math. And this term means you are dividing this number 30 by the modulus 12 and whole numbers and just finding their remainder. So here it's 2 times 12 plus the remainder gives you a congruence with 30. And this same concept applies to any number. 4 times 12 is 48 plus 2 equals 50. So the answer to 50 modulus 12 is 2. And now back to Euler's theorem. Do a couple of examples to show this. So we have two numbers that are co-prime. So one number would be 33, and the other number could be any one of these. So these two numbers that are co-prime. So what his theorem is saying is we pick any one of these. We take any number. We can raise it to the phi of m, and the result is going to be, we're always going to get a remainder of 1 when we do modulus of the prime number. So in this case, 2 to the 20th gives us, it's the same thing as saying 31,775 times 33 plus 1 gives us 2 to the 20. And the same thing is going to hold true for this example. Raise 4 to the 20. We get this number, which is the same as this number times 33 plus 1. So the remainder is always going to be 1. So that is this equation here. This equation is we know to be true. So now let's start putting these relationships together. And in the RSA process, just as a consideration in RSA, your message size has to be less than your n. But by the steps now, we pick 2 large prime numbers, we calculate n, we calculate phi of n. And for step 3, we select a public number e, and we determine d. We'll do an example of this here in a second. But Alice takes Bob's public key. She takes her message, she takes Bob's public key, and she creates a ciphertext message using her message raised to the power of e, which is Bob's public key, to the modulus n, also his public key. And only Bob, that has the key d, which is, as we know, related to e, can decipher this and get back the original message. So an example, so we have this p, q, and n, and phi of n. And now on to our e and d. And e must satisfy these conditions. It has to be relatively prime, doesn't share a common divisor, and so on. So all we have to do is pick one of these. So we'll pick e as 3. I'm going to change the layout of the slide here. So now our last step is to determine what d is. And we have this unusual looking equation, and this has to do with the modular framework. This is just a way of looking at the relationship between e and d. And finding d here, it looks unusual. This has to do with what's called group rules. We won't get into the details, but d and e have to have what's called an inverse group relationship. And we're looking for a number that when you multiply e and d together, the result is 1 more than the multiple of your modulus. So 1 being your remainder. E times d is the remainder, here your modulus phi. And a d of 27 gives us that. So we've got our e now and we've got our d now. And also the relationship here is still obscure. These are trivial small numbers. 3 can be public knowledge, but your d here and your p and your q all are still, they're still kept a secret due to the integer factorization problem. And then for the last steps, again, everyone in the world has Bob's public key. Alice takes the public key, uses this equation to calculate her ciphertext. It gets 13 to the 3 is this number. This number is 39 times 55 plus 52. So her answer is 52. This 52 is the cipher message. She sends this message to Bob, and he is the only one in the world who knows what d is. So he takes 52 to his secret d. So 52 to the 27 is a really large number. It's the same thing as this really large number times 55 plus the remainder, which happens to be 13, which is the message m. He gets back the original message. And there is the mathematical relationship between this encrypt, decrypt, n, and phi of n. And that's what makes this equation down here possible. So you take m through this equation, you get back the same number. And we have this public number, e and n, and we have this secret decrypt number, d. So more on this. These two equations are the same. This is the example we just walked through, and we know this is the answer. This equation is the same as this one, and we'll walk through that. So D, we know D, we know E, 13 to the 81 is this large number. Is also this large number times 55 plus the remainder of 13. So we know these equations are the same. And the math proof that we need to do now is not that straightforward. So every mod equation has a congruence and it allows you to ignore multiples of n. So you raise this expression to some power or any power. Raise this expression, I'm sorry, to some power, to any power, and it can just be reduced down to this expression, because no matter how many times you loop around the circle, the congruence is not gonna change. So the exponential increase in A is still going to be divided by the modulus. We still end up with just this equation. So now back to D and E. You know, this process you go through to satisfy this equation, it's just a guess and check process. But this equation must be true, and this is what ensures E and D have the property of being a multiplicative inverse modulo phi of n, and they have to have that property. So now let's review the facts that we have. Our message is between 0 and 55. And P and Q are both primes. Shuffle the slide. So to get into the specifics of why this works and this proof, we'll start with Q. So Q of 5, for each number that the message could be, Q is either going to be Q is either relatively prime to the message or evenly divides by it. And likewise for P. So let's start just with Q first. And let's start with Q, and the relationship between Q and M is relatively prime. Then we have these equations here, and we can say this. So reshuffle these. So this brings us to these two expressions that we know to be true. And now we have all of our RSA components are now in one place, and we can prove the relationship and bring them together. So this equation here, this side of the equation, if we just use rules we know of exponents, we can turn it into this equation here. And then we go to M of Q minus 1. Well, there's this relationship between Q minus 1 and the phi of n. So because the Q minus 1 is just another, it's another divisor of phi and n. It's just another, or it can be also considered another multiple of phi of n, but it's not going to change the congruence. So we can take out the Q of n and just call it the phi of n, and we can do that because it's going to have no impact to the overall congruence of this equation. So these two, we can trace this down on both sides, and we're going to arrive at the same answer, which is what this is right here. And so this expression is the same. So and now we have this expression. These two have been combined. We know this to be true. And then we do a little more math on what this looks like. We're getting close here. And now moving this up. So what we just covered was we proved this if we know that M and Q were coprimes. So now let's look at it as if we happen to have a message that is divisible by Q, and it doesn't matter if they are divisible. The left side of this equation will still produce a number that is perfectly divisible by this side. So you might need to think about that for a second, but the congruence here is always going to hold even if Q is M and Q are not coprimes. This equation is still going to hold. And we do all of this again We did all that for Q. We do it all again for P. We get the exact same results. It's going to be, doesn't matter what the value of P is, doesn't matter what the value of M is. This equation applies. And I'm going to skip over a bunch of math, but we know, if we know these two equations, then we know that this equation down here on the bottom is also true. So this takes us here. This is the relationship between all of our variables in the RSA protocol. And this is what we set out to prove. I know that was a clunky few minutes of video, but we have our public variables, our secret variables. They're all mathematically related, and they can be used for a public key protocol. So RSA is based on an intractable math problem, a one-way math problem, and you can leverage the special modulus properties of prime numbers. You have secret variables and public variables tied together in these relationships. So anyone in the world at any time can send a cipher message to Bob, and the only way to decrypt that message is to have the secret number D that corresponds to the public key that was used.